So I'm going to try it with video on this machine. Usually it's a little bit slow, but we'll see. Hopefully everybody can see me. No, you can't see me yet. Let me start up the correct application. As you can tell, I'm significantly more ready for this to happen this time. I thought it would work because I updated this computer, or the other computer rather, but it didn't work, so we'll have to deal with that. Also, that computer writes a lot more nicely than this one, so I was really hoping that I would be able to continue doing that, but we'll have to deal with it. Anyway, hopefully everybody's here. We are recording, I believe, so let's continue. Right, so right, so it's the center of mass of the object let me just back up just a minute. So the location at which the force is applied it doesn't matter. At least not until we start talking about rotation. So really, so then the question is what part of the like if it doesn't matter if you push on the top. Yeah, so it was discounting rotation. So like if you the picture is if you have a rod freely floating in space, push on the top, it's going to start rotating. It'll also start moving while it's rotating, but we're not going to worry about what happens with the rotation yet because it takes a little bit more machinery to get there. We will talk about that later in the course, but just not yet. So the question then is you can push wherever you want. The location where you push on the rod doesn't actually affect the equation A equals F over M. So the question is, if it doesn't matter where you push, then there should just be one place that accelerates at that rate, regardless of where you push. And the question is where is that location? So it turns out that it is the center of mass of the object. And we will define center of mass rigorously later, but it's the center of mass of the object that is what accelerates when forces are applied. So the rest of the object just kind of follows along with it. So what we do then is we can reframe Newton's second law one more time, and we can write Newton's second law in its final form as the acceleration of the center of mass. So this is, you measure the coordinate position of the center of mass, and then you take 2 time derivatives of that coordinate position. That is equal to the net force divided by mass. And so the center of mass of most things is going to be fairly intuitive. Like the center of mass of a uniform rod is going to be about the center, right? Center of mass of a sphere is in the middle. Center of mass of various things is roughly in the middle, assuming that the mass is uniformly distributed. But for the most part, because we're discounting rotation, we just treat everything as if it's just a point located at its center of mass. And that point is the thing that's moving. Now, in reality, this whole system is going to move to the right. But the top is going to move to the right a little bit less than or a little bit more than the bottom. And so the whole thing will rotate. But the center of mass will accelerate at some rate, and that rate is given by Newton's second law. Now, by the way, there's a reason I've written it this way rather than F equals ma. And the reason for that is because if you write it as F equals ma, you kind of are implicitly, is the center an average or the top? The center of mass is kind of like an average. It'll be lower than some parts and higher than other parts. Yeah, so the reason we write it this way rather than F equals ma is because if you write it as F equals ma, you might be inclined to think that mass is something that the object has, acceleration is something that the object has, and so if you multiply those 2 things that an object has, then the force is something that the object has. But that's not what it is. And I want to kind of get you away from thinking that way. So instead, we write it this way. We say that the force applied to an object divided by a property of the object, that gives you the acceleration. It's the force that causes the acceleration, but the force is external. So it's just something to keep, it's just writing it in a way to keep it straight. But when you're using it in reality, you're going to be using it as F equals ma. This is just a nifty way to write down the equation. Now, just as a quick side note, The force diagrams kind of play nicely with this, right? Because the force diagrams, it doesn't matter where you draw the force arrow. All that matters is that you draw force arrows in the correct direction. And that's because the only thing that it cares about is the only thing that Newton's second law cares about is the acceleration of the center of mass. So if you put the force arrows wherever you want, it doesn't actually matter. That's why you can do that. And the reason why we like force diagrams to begin with is because once you draw out all of the force vectors on the force diagram, then you can actually use geometry to figure out their components, add them up to find the net force, and then you can divide by the mass to get the net acceleration. So let's put all this together. Actually, I'm not even going to write a whole lot for this because it's just a ton of examples and I'm not going to go over them. But there is the idea behind Newton's three laws, is really you're basically just going to be using the second and the third one for the most part. And really your most useful tool will be Newton's second law. You'll draw a force diagram. You'll figure out all of the forces on the object. Remember, using this force phrase rule, type of force, on blank, by blank, or from blank. You will draw your force diagram. You'll add up you'll figure out what the components of those forces are from your force diagram using standard like trig and geometry and things like that. You'll add them up and then you'll apply Newton's second law to figure out what the acceleration of the object is, or vice versa. Maybe you know the acceleration, but you don't know one of the forces or something along those lines. Newton's third law comes in when maybe you know a force that the object you're interested in acts or applies to another object. So you have to use Newton's third law to figure out the force that the object you're interested in feels from the object it's acting upon, right? Sometimes you might not know all of the forces on the object you're interested in, but you can figure them out using Newton's third law. Now, there's a whole bunch of examples that I listed in the lecture notes. I think I posted, that's 5, there, wait a minute. Yeah, there's 10 links to the Rice University textbook with just a whole bunch of force diagram problems and Newton's second and third law problems and so on and so forth. There's also just things to think about that I wrote down in the lecture notes. These are things like, what happens if you pull on a spool of thread? Will it unwind or will it keep moving? Or, these are things to think about. We can talk about them in ops hours if you'd like. There's also a few examples in the Libre text. And then at the very, very end of section 2.2 in the Libre text, there's a relatively good summary, I would say, of all of Newton's laws and how they kind of all fit together. So I would suggest you take a look at those. I'm not going to go over it because I would just be copying exactly what's in there, but do take a look. It'll help you maybe conceptualize the whole thing. So with that out of the way, we finished Newton's three laws. So we're going to start getting into applications, and this is where we actually need to start talking about what types of forces are present. So let's do that. So before we actually jump into force, I want to dispel a, not a myth, but like a misconception, right? So let's talk about this notion of inertia and the notion of static friction. So hopefully, well, you guys might be too young for this, but hopefully you guys all know that inertia is a property of matter. But also it's more than that, right? So let's talk about what inertia is. So inertia, by the way, is literally just a synonym for mass. Like that's all it is. But what it isn't, it is not something to be overcome to keep something from moving. Like you might say, oh, this thing, I have to overcome the inertia to get this truck moving. So it takes a lot of power to get this truck moving because it has a lot of inertia. That's wrong. Like you're not overcoming inertia. That's an incorrect notion. Inertia literally is just mass. It's an old term for mass. But it kind of got this this misconception that it's something that you overcome. So I want to dispel with that myth right away. But still, there is something to be said that heavy things do resist motion more than lighter things. So the question is what exactly is it that is resisting? What exactly is it that makes it hard to push a large block of stone? And the answer from the heading should be fairly obvious. It's friction. In particular, it's static friction. So static friction is related to mass and hence related to inertia, but it's not mass, it's not inertia. And this should be fairly easy to see, right? So we know that slippery things have less friction than non-slippery things, like ice has really low friction. You guys probably have that intuition already. I would bet that you get the strongest man in the world, or maybe even just a regular person, I would bet that if you put a 747 jet on a really clean like ice rink, I would bet that person could push it, because it doesn't take a whole lot to get it moving. Like there's almost no friction. We will get to the coefficient of friction. So the point is inertia is just mass. I don't want to see anybody saying, oh, you're overcoming the inertia of a thing, or oh, it has so much inertia it's hard to get moving. If you replace the word inertia with mass, then you'll be less confused and you'll be less likely to be wrong. So just getting that out of the way, let's start talking about forces. In particular, what types of forces there are and their specifics. Yeah, assuming that the dude has like ice spikes in their shoes or something. Yes, of course. So first, let's kind of talk about gravity and air drag, or air resistance. So I gave you this example. I showed you this YouTube video of a guy on the moon dropping a hammer and a feather, and them hitting the ground at the same time. Now, the reason for that was just that everything accelerates at the same rate due to gravity. And the question then is, why is it that you might think otherwise, right? So I think it was Aristotle that initially thought that heavier things fall faster than lighter things. And that's not a bad observation, right? If you drop a lead ball, it's going to fall really fast. Whereas if you drop a ball made out of styrofoam, it won't fall nearly as fast. So, if you're just doing observational science, you might say, well, heavier things fall faster than lighter things. So the question is why does that happen on Earth? And it didn't happen on the moon. Now, you guys already know the answer. It's because the moon is nearly a perfect vacuum. In fact, I believe it's better than the best, or it's nearly as good as the best vacuums that we can get on Earth. And those vacuums occur in really small regions, whereas the moon is really big. So it's the best, largest vacuum that we have access to. And so that's why they fall at the same rate on the moon. They don't fall at the same rate. A feather and a hammer don't fall at the same rate on Earth. So we're going to kind of quantify why that happens. So we're going to answer the question, why does a hammer hit the ground before a feather? And it wasn't movie magic, by the way, because the moon landing was not faked. Or was it? Right? So we're going to consider two things. We're going to idealize this scenario, which we do in physics a lot. So we're going to instead consider two otherwise identical objects with different mass. So imagine, you have two spheres made out of some material that's painted black or something, and one of them is made out of lead and one of them is made out of styrofoam. So they're identical in every way, with regards to their shape and so on. The only difference is that they have different mass. So one of them is denser than the other. So we already know right away, just from observing, that we know that the acceleration of the light object is going to be less than the acceleration of the heavy object when falling. And this is due to drag. It's due to air resistance. So I've already told you that. But you could test this by creating a vacuum chamber and then testing it and reintroducing air, introducing a single variable, right? So we can quantify this with Newton's second law. So already we know that the force of gravity divided, say, or let me write it this way. So the acceleration due to gravity on the heavy ball would be, we know that this is, where'd it go? Would be equal to the force of gravity on the heavy ball. I'm going to just call it force of gravity on the heavy ball, subscript GH, minus the force of air on the ball divided by the heavy mass. So the picture that we have here is we have we have two balls. One of them's falling, or they're both falling. They both experience the force of gravity. And they both experience a drag pointing upwards, force of drag. The question is we want to understand why this happens. Well, we know that this acceleration of the heavy ball is larger than the acceleration of the light ball. So this should be greater than, and by the way, the coordinate system that we're choosing for this description is we're choosing that down is positive. So this acceleration of the heavy ball should be larger than the acceleration of the light ball. So the force, the net force on the light ball is the force of gravity downwards plus the force of drag upwards. And there's a minus sign because they point in opposite directions. So it's the force of gravity on the light ball minus the force of air. And we could even call this on the heavy ball and this on the light ball. It doesn't actually matter. This is divided by the mass on the light ball. And this is equal to the acceleration of the light ball. Now we know that if there was no drag, the acceleration would just be g, right? So we know that the force of gravity on the heavy ball divided by the mass of the heavy ball, that should just be equal to g. And similarly, we know that the force of gravity on the light ball divided by the mass of the light ball should also be equal to g, right? If there were no drag, then they would just both accelerate at the same rate. So if we ignore this term, they should both have acceleration equal to g. So that means that the acceleration on the heavy ball is equal to g, I'm just plugging this into this equation here, minus the force of drag, force of air on the heavy ball divided by the mass of the heavy ball. And the force and the light acceleration, the acceleration of the light ball is also g minus the force of gravity, sorry, the force of drag, force of air resistance or drag on the light ball divided by the mass of the light ball. Now, it turns out, and we will see this later when I go into more in depth on drag, it turns out that the force due to drag doesn't actually depend on the mass of the object. So the reason why, in particular, these two forces would be the same. They'd be the same between the heavy and the light ball. So the reason why the light ball accelerates less is because the denominator of the term that drag contributes to is smaller. So when you divide by a small number, you get a bigger number, which means that this term contributes more to the acceleration than this term does because they have the same numerator, but their denominators differ. So it's not that things fall faster when they're heavier. It's that drag pushes relatively more when they're lighter. And this makes sense. A styrofoam ball is going to fall more slowly because the air that it's knocking back the air at the same rate that a lead ball is, because a lead ball and a styrofoam air are both the same size. They're knocking back air at the same rate. But the styrofoam ball gets pushed back with the same force, but it has less mass to resist that force. Hence, we get this effect that lighter things fall more slowly. Just as an observation, by the way, if there's no drag, we know that the acceleration should be zero. Sorry, the acceleration should be g. So what does that imply? It implies that the force of gravity on any object is just m times g. You take g, which is just a number. By the way, this is the magnitude of the force of gravity. It's just g, which is 10 meters per second squared, and you multiply it by its mass. And that value happens to be the gravitational force that an object feels. So this is a useful equation because anytime you have the force of gravity involved, you're going to need to, you will likely need to know the magnitude of that force, and you also might need to know the direction. The direction's obvious, it's downward, but you'll need to know the magnitude, and the magnitude can just be found by multiplying the constant g by the mass of the object experiencing that gravity. Right. Oh, why is there, okay, so I need to fix my lecture notes because it's duplicated. All right, let's talk about tension. So that's gravity. Gravity, force of gravity, mg. Easy peasy, done. Next force that was on the list, tension. So tension is a pulling force, usually from a rope or a chain or string. Basically, if something is being pulled taut, that thing is experiencing, or that thing can exert a tension force. So when we're talking about tension, at least for the sake of this, for the early part of this course, we are going to usually assume that the string, the rope, the chain, or whatever, that those things are massless. And the reason we do that might not seem clear to you yet, but it is a really powerful assumption. First of all, in real life, ropes are not very heavy compared to the things that they pull, right? You can lift a human with like quarter inch climbing rope. Like the rope doesn't weigh very much. It just has a lot of tensile strength. So, to a good first approximation, ropes and chains and strings just are massless compared to the things they're attached to. But more importantly, by assuming that the rope is massless, this allows us to treat ropes as conduits. And I'm going to put this in quotes. Conduits. Let me just stretch this down. Treat rope as conduits to separate third law force pairs. Put another way, ropes basically function as a way of transferring force across a distance. So the question is how? So why is it that if we assume the rope is massless, then we can just do this? Well, remember that the net force on an object is the mass times the acceleration, right, of the center of mass. By the way, sometimes I'll drop net or I'll drop cm, assume it's there. So if we're interested in the force, or if we're interested in the acceleration on the rope or the force on the rope, a conduit is just like, it's like a way of transferring for free. Like it takes an input and then it puts an output elsewhere. Think of it like a pipe or a wire. A wire is a conduit for electrical signals. A pipe is a conduit for water. So basically it allows you to pull on one side and then the other side feels the same pull, right? So the point is if the mass is 0, then, assuming nothing's infinite, then the net force is always 0. Assuming, assuming that the acceleration is not infinite. So what that means is this implies if the net force on a massless rope is always 0, it means that the two forces on either ends of the rope, maybe two people are pulling on either end of the rope, they have to cancel. So if you have one person pulling on the right end of the rope, another person pulling on the left end of the rope, then because the rope we assume is massless, the net force on it is 0. So the force that person A pulls on the right end is equal and opposite the force that person B pulls on the left end. And so that means that, so even though they're not actually third law force pairs, they act like they are because they're equal and opposite. And really what it is it's the rope that, let me draw a picture. So you have person A, or so you have person A. I'm going to draw a free body diagram for all of these. You have the rope and you have person B, right? So person A is pulling on the rope. This is force of person A. They're pulling on the rope. So from Newton's third law, the rope is pulling on the person. Usually we'll call that a tension force, by the way. We'll call that the tension force on A. Person B is also pulling on the rope. And so person B feels a tension force, equal and opposite tension force from the rope, right? These are third law force pairs. But the important point is that FA is equal in magnitude and opposite FB, because the net force has to be 0. And so what that means is it means that TA is equal in magnitude to TB, and they point in opposite directions. So it's like these two people were just tugging on each other's hands. It's like they're third law force pairs, but the rope kind of lets them separate from each other while still being in contact via Newton's third law. That's what ropes let us do. And that's really powerful, especially because when we do this, i.e. i.e. treat ropes as if they're massless, the third law force pairs aren't always opposite directions anymore. Or at least they don't have to be. Yeah, we'll get to the pulley. And yeah, this is precisely when this happens. If you have a pulley, you can transmit that force around for free. So the picture is you have a block maybe that has that's attached to a rope, sitting on a, I can't draw today, sitting on a flat piece of ground. There's a pulley, and the rope goes around the pulley. Now, the force here and the force here, so those two forces, downside of using this machine is that it's harder to get, maybe I can do that actually. Oh, no, that's bad. Sorry, one sec. I'm just trying to make it so that I can change colors mid. Nope, can't do that. Can I make this go away? Okay, that's not bad. These two forces can be treated as third law force pairs. And yes, the arrows are correct. This is not motion. These are the forces. So the top block is going to feel a tension force pulling on it to the right. The bottom block is going to feel tension force pulling on it upwards. And those two forces are roughly equal and opposite. They're not actually opposite because they point in the same direction, but they are the same in magnitude, and they behave as if they were equal and opposite. So in that sense, ropes can be really useful. They don't point in the same direction. That's the important point. You can use a pulley to redirect the tension force that a rope or a wire or whatever would conduct, but they still can be treated as if they're equal and opposite, because if you increase one, the other will increase by the same amount, and the directions are just determined by the geometry of the rope. So for the sake of not the remainder of this course, but at least for now, we're going to idealize pulleys the same way we idealize ropes. We're going to assume they're massless and frictionless. Not that the magnitudes are pretty much the same. The magnitudes are the same. Right. Another force that we should talk about is the contact or normal force. So the contact or normal force is a weird one. It's a balancer force. So what I mean by that is it's not really determined by some external criteria. It's actually determined by the other forces that are present and the motion of the object. So this balancer, what it really means is it provides sufficient force to prevent objects from passing through each other. So the contact of the normal force is the thing that stops you from falling through the floor. If it weren't there, you would fall through the floor. You would fall through your chair, you would fall through the earth, you'd fall through stuff. So the contact or normal force is just all of the combined effects that keep you from falling through stuff. So the picture is, you have a block sitting on a desk, say. You have a force, so the block is going to experience a few different forces, or in this case, it'll experience two. It'll experience the force of gravity, pointing, say, downwards, and it will experience a force from the table pushing up on the block. Yes, this is the one that's perpendicular. It's perpendicular to the interface. So notice that the interface moves is left and right. Oh boy, the interface is left and right. So the normal force, normal meaning perpendicular, the normal force is perpendicular to that interface. So the normal force, in this case, pushes up, also called the contact force. So in this case, if the block is not moving, if the block is stationary, for example, that would be an example of not moving, then the acceleration, by definition, like if a thing's just sitting still, its acceleration is 0, right? But what that means is it means that the net force is also 0. And so if we were to figure out what the net force is, if this normal force wasn't there, it would just look like, yes, normal and orthogonal are synonyms. Yeah, they are literally synonyms. If that normal force was not there, then the net force couldn't be zero because there's only one force. How could it be zero? It's just the gravitational force. So the normal force is there to cancel out the stuff that needs to be canceled out. So in this case, we would find that the magnitude of the normal force is equal to the magnitude of the gravitational force, even though they point in opposite directions. So the point to make here is that if an object is not accelerating perpendicular to a surface, so imagine an object just like sliding along a surface, right? Then there has to be a normal force ensuring that the acceleration in that perpendicular direction is zero. Because if it weren't zero, it would either float up or it would sink through the surface. There has to be a normal force. So when you're doing these sorts of problems where there's a whole bunch of forces involved and you have a block sliding down a ramp connected to a rope with a pulley and blah, 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 blah. When you're considering what types of forces could be present, first of all, generally you want to consider, there are cases where the normal force is not equal to the magnitude of the gravitational force. That's certainly possible. Generally, you want to consider, obviously you're going to want to consider gravity, right? Gravity is almost always there unless stated otherwise. And then you'll want to consider, okay, well, what is the object that I'm interested in actually touching? Because anytime that you have a point of contact between two objects, you can have a normal force. In this case, the object is touching the block is touching the table. So there's potential for there to be a normal force pointing away from that point of contact. And so you would have to consider that. And then you could find the components of that normal force, and then you might have to solve for those components or use the magnitude, which you already know in a different way, and so on and so forth. But when you're trying to figure out what forces are present, the first thing to consider is what's touching the thing that you're interested in. Because besides the fundamental forces, the only things that can actually provide forces are things that are touching the thing you're interested in, right? There has to be a contact between the two objects. Right, friction. So that's normal force, by the way, and it's going to show up a lot. So will friction. So there are two types of friction. We're going to try to talk about both. There's static friction, and there is kinetic friction. Right, so let's talk about kinetic friction first. It's a little bit easier to wrap your head around. So kinetic friction is exactly as it sounds, kinetic meaning moving, friction meaning rubbing. So this is when you have two surfaces rubbing together. Think like a piece of metal and sandpaper, for example. It's hard to push a thing along sandpaper because you have two things rubbing together. So it's a force, so it has a direction because it's a vector. So the direction is the direction that opposes the rubbing or the sliding motion. Now, that does not mean that that the force points in the direction to reduce motion. It just reduces relative motion. So if you have two things, let's say that this thing is moving with some speed v over a surface. In that case, there would be a friction force F sub k pointing backwards because the block is rubbing against the surface. So there would be a friction force opposing that rubbing and sliding motion. Importantly, by the way, though, the table will feel a frictional force pointing in the opposite direction because from the block's perspective, the table is moving to the left. And so the table should experience a friction force pushing it to the right. So by the way, just like gravity, the contact force and both friction forces also have third law pairs, right? If a block like these two forces here are third law force pairs, right? One of them is the force of friction, the force of kinetic friction on the block from the table. The other one is the force of kinetic friction from on the table from the block. By the way, if you're going to ask a question, make sure it's public, otherwise I won't answer it. The magnitude of the kinetic friction is just a relatively easy thing to compute. So the magnitude, often we just write F sub k. This is not a vector equation what I'm about to write. This is the magnitude of the kinetic friction force. This is equal to mu sub k times n. So n, oh, I should have mentioned that earlier. The contact force, often just called n. With a vector to indicate it's the normal force. So what I'm saying here is the magnitude of the friction force is directly proportional to the magnitude of the contact force. So if you push down, if the table is pushing up harder on the block, then the kinetic friction will be greater. That kind of makes sense. If two things are pushed together really hard, there's going to be more friction between them than if they're not pushed together very hard. And that contact force, that normal force, tells you how hard the two objects are pushed together. So this mu sub k, this is just a number. Mu sub k, it's called the coefficient of kinetic friction. And that, it's just a number. It's a unitless. It doesn't have any like units associated with it. And it basically describes how rough are the surfaces. Sandpaper has a very large coefficient of kinetic friction. Ice has a very small coefficient of kinetic friction. This n here, this is the magnitude of the normal force. So if this block is sliding to the right on the table, it's going to experience a kinetic frictional force pushing to the left. That's this one. But Newton's third law says that for every force, there's an equal and opposite force. So what that means is that so there's one force, which is the force of kinetic friction on the block from the table. The third law force pair would be the force of kinetic friction on the table from the block. And indeed, it points in the opposite direction, has equal magnitude, and it is a force on the table. If a thing is slowing down because of friction, the table is being pushed a little bit in that direction. We can talk about that more in more detail later if you want to, but I do need to keep going because I want to finish friction before the end of today's lecture. And that might not happen. Do objects experience both frictions, like static friction up until a certain point, and then when it moves, slides, or something, it becomes kinetic? Yes, that's exactly what happens. Yeah, and we'll get to that once we start talking about static friction. So the normal for this n is just how hard the objects are pushed together. Yep, and it's exactly equal. It is the magnitude of the contact force, of the normal force. But just to be clear here, this is not a vector equation because they point in the wrong direction, right? The normal force points up. The kinetic friction force pushes, points left or right. This is just an equation about magnitudes. All right, last thing that we'll cover today is static friction, which is just the slightly more confusing older brother, I don't know, younger brother of kinetic friction. And so the static friction is just a reactive force, like the contact force, that acts to prevent touching objects from starting to move relative to one another. So if this block were originally at rest, then we know that you have to push past a certain threshold to get it to start moving. If you just lightly tap it, it's not going to start moving, even though you're applying a force. And that's because the static friction will match whatever the applied force is until some threshold is met. So this is the cause of that inertia that we talked about earlier. So again, just like the contact force, static friction is a force balancer. And so it has a maximum value. We say that the magnitude of the static friction is less than or equal to the coefficient of static friction times the normal force. So this mu sub s, by the way, that's a Greek letter mu. It's not a u. It's like an m, but it's Greek. Coefficient of static friction. So just like how we had for the kinetic friction case, we have a formula that relates the magnitude of the kinetic friction to the normal force. Here, this tells us what the maximum amount of static friction can be provided. And the reason there's a maximum is because you can push with all the way between 0 up to, say, 5 newtons on, here's a cup, right? You can't really see that. Here's a cup. If I'm pushing on it, it's not actually moving. So I'm just barely touching it. I'm pushing it. Eventually, it'll start moving as I increase that force. And that force that I pushed on is greater than the maximum possible frictional or static frictional force. Yeah. Fs. This is again a magnitude of the force. The force still points in the direction that is opposing. Yeah, that was an Overwatch Cup. It does point in the direction that's opposing the relative motion. So if I'm pushing this way, the coefficient of, or the static frictional force will point to the left until it's overcome. Once it's overcome, it becomes kinetic friction, and the static friction just goes to zero. But the point is, and I just want to clarify this. So the static friction will equal the attempted pushing force until it reaches its maximum value. Once it's reached its maximum value, you can just keep applying more force, but the static friction can't counteract all of that. So the static friction will just be whatever it is, and then the object will start moving because the net force is no longer zero. Once the net force is no longer zero, it starts moving, and so the static friction becomes the kinetic friction. Once the applied force, and I know we're done, is greater than mu sub s times n, then the static friction becomes kinetic friction. All static friction goes away because the object's moving, and the kinetic friction takes over and becomes the dominant force when we're talking about slowing objects down. So the question then is why is it hard to slide heavy things? Well, and this will be the last thing answering this question. Well, the answer is relatively straightforward. So assuming only gravity is present, just like an object's just sitting there, it's not like in some complicated setup, then the maximum that the maximum static frictional force is equal to mu sub s times n. But if it's just gravity, if gravity is the only real force that's acting on the thing, you're not lifting it, you're not pushing it, whatever, then you have a force of gravity downwards and you have a normal force upwards. And then you might, if you're pushing on it, say to the left with a force F, then there would be a static friction force pushing back. And so the object will not start moving until F is bigger than the maximum possible F sub S. And so in that case, the maximum possible F sub S, it's just equal to mu sub S times N. And if gravity is the only up-down force besides the normal force is just the force of gravity. And so the point is that if the mass is greater, then the maximum possible static frictional force is larger. Implies larger F sub S. So you have to apply a larger external force to get it moving. And so that's why heavier things have more inertia. So I'm going to end the lecture there. I know I went over, and I know I've been going over a lot.